Hi, Victoria. How are you?
Good morning, Katarina. I'm well. How are you doing?
Really good. I had a good morning today. I'm working from home.
Fantastic.
Yeah,
That's the best.
could sleep a little bit more. I had migraines the last few days, and they are gone now. No, I'm having a good morning. Thank you.
Hallelujah.
Yeah.
May they always be gone.
Yes, exactly. Hi, Brian. How are you? Thanks for coming. Hi, Diego. Hi, Catherine.
Good morning,
Welcome.
Brian. Good morning, Diego, Catherine, Rabi. Goodbye, Rabi. Welcome, Rabi. Rabi's having issues.
Do you like the topics wheel of time? Do you think that's appropriate? I'm not sure. There's no time
I love
crystal.
that. Let's see. Wait. Wheel of time. Yeah. That's great. Why does engineering have pizza? Because engineers eat pizza?
I don't know. It's so weird, isn't it?
Because you have to figure out where to put the things, the toppings.
It's I think I asked somebody already, but nobody knows.
Maybe we need to Google, there might be a famous joke about engineers and pizza. Like, how many engineers does it take to make a pizza? We just don't know
Yeah,
it.
could totally be.
Hello, this is Raghav Sharma from India.
Hi, how are you today?
I'm good.
We will talk today about physics and time crystals. So we are waiting for our guest speaker for a few minutes.
Okay, but
So he will.
I'm a magician and a fashion photographer. So I think
Oh, you should have come yesterday when we had the room about using gold and DNA, like using tiny gold particles and DNA in a gel to change colors. Because we talked about how we could maybe in the future make like the skin patches that change color or textiles or clothes in a very cool way. That would have been interesting for you probably. But yeah, feel free to learn today about time crystals. Oh,
yeah. Thank you so much, Katerina, for inviting me. Uh, do follow me back. I'm gonna follow you guys.
yeah, sure. And Brian, that's a good answer because of the triangle. That's because it's an interesting, with interesting angles. So yeah,
Oh, yeah. That's
that's
a
a good.
great answer.
So what you guys doing for living? Like,
I'm a scientist. I'm a senior scientist at the company and assistant professor at NYU. And yeah, Victoria, you answer for yourself.
Hi. I work in
amazing.
Oh, go ahead. You were speaking?
Lots of respect for you guys, Katerina and Victoria. You are the future for our Earth.
Well, thank you. That's very kind.
So, what type of photography do you do? Oh, fashion photographer,
I
I
do
see.
fashion photography and I do music videos as well. I'm a DOP.
Okay, interesting.
I'm in this field
My son.
like for 8 years and I'm 22-year-old. So I do fashion photography or photography from my childhood, like from 11, 12.
Oh, wow. Yeah, my son, he's a music producer, my first son, and about your age. and he also makes music videos. So interesting. You guys should connect. My son is here in New York City, having a studio and making music videos too. So that's interesting.
Okay, okay.
And he always criticizes me how I dress. Like he is, he's so good at matching styles and colors, and I'm the typical. Well, not typical, but a little bit more the nerd that doesn't have patience every day to care about how I dress. So
Yep,
That's
yep.
really fun. That he's. I hope he's more critique and less like criticism.
yeah.
Like he gives. I hope it's ideas. Hey, good morning, Ryan.
Hi, Ryan. Hi. Yes, both
Okay,
my
good.
sons are, and my daughter's very good at that too. She actually dresses her on her, like she makes her own dresses now sometimes. So my kids are very stylish, and yeah, the sneakers, for example, they choose
Do
them
tell
for
me
me. I have
their
no
names.
say.
Do tell me their username. Do tell me their username in comment
Oh
box.
yeah, I will. I will. I have to. I have to check them. Well, my middle son and my daughter, they are younger. My daughter, she's 8, she will turn 9, and my middle son, he's 12. But they are very good at choosing, styles and stuff. Like my daughter gets compliments all the time about her, clothes, and I never. But I get compliments since they choose my shoes. I get compliments from my shoes now, from my sneakers, from various colleagues that are younger than me.
If you keep talking about your
Evening,
sneakers, we're going to
everyone.
need some
Hello.
PTR. Good morning, Jamie.
Hey, Victoria. How are you?
Yeah, hey, how are you? We are having a very non-scientific discussion about styles and fashion because we had a fashion photographer from India here talking with us, passing the time.
I thought we were prepping for a photo shoot, honestly.
Sorry about that. I was switching my Wi-Fi over. That was quite a bad connection. Can everybody hear me okay now?
Yes. Yeah, Ryan, that's
Awesome.
good that you've chosen that shirt for today's talk, considering we had the fashion photographer here. I'm glad that you're making such wise decisions. Sorry, Jamie Ryan is wearing a powder blue button-down shirt, recently pressed.
Hi,
Very
Sam.
nice.
I invite. Oh, there you are. Welcome. Meet our team. Um, meet
Hello,
Jamie.
can you hear
Victoria.
me?
Yep, we
Oh,
can hear you.
hello. Welcome.
Very good, thank you.
Good morning.
It's yeah, I guess it's morning over
Oh, good day. Hello. Welcome.
there.
I'm in Scotland, so we're in the same time zone at least.
Yes, yes.
Jamie, I'm Jamie.
Where are you?
I'm in actually at home today in Lancaster,
Oh, nice.
which is close to Manchester.
Yeah, pretty.
Is it pretty warm over there just now? It's been decently warm here, but I heard that over there where you are just now is pretty warm.
Well, Lancaster is right at the coast, so it's never very cold. It's never very hot. It's almost always raining.
Nice.
Um, but yeah, well, I mean, I haven't been out in the past 4 hours or so, but that's at 12. It wasn't very warm, maybe 18 or something like that.
Ah.
But it's a working day, so it doesn't really make any difference.
Absolutely not. Anyway, you're about to talk about some very high-minded science. That's where our minds are going to travel. They're going to go out beyond what we know, and that's as much as out as we can expect.
Yes.
We already commented that your bio has the coolest questions in the world.
Well,
Doesn't get cool.
it's an advertising business, if you wish. I mean, I don't like that, but that's the way it works. Like when you trying to get your stuff through in fashionable journals, or especially if you're applying for Anglo-American fellowships, then cool stuff is what you need. And while that isn't necessarily always the most efficient way of describing what the research is about, it makes people interested. So that's a necessity.
Oh, Katerina, was this with the question that you put on the chat with us? Can you melt a time crystal or something? Was
Yes.
it you said?
Yes.
Do you know, Dr. Katerina had put this question out yesterday, and I just thought she was randomly asking it herself. I didn't actually know this was part of
No, I did.
what
I
you had
said
on there.
check out the bio. Like I shared the bio, and then I
Okay,
pointed out the question.
Okay, that makes sense now, because that was an incredibly cool question. Can you melt one of these things?
Yeah, well, so of course it's a nice way of asking things, but it turns out it also mathematically makes sense, and I will talk about that in a moment. Well, originally time crystals came about as an outcome of a mathematical adventure, if you like. Well, Frank Wilczek basically was asking whether the concept of spontaneous symmetry breaking can be applied to the time domain, just like it is applied to many other domains like space and various other things in phase transitions. I will explain what all that means, but if you follow this logic, then it makes also sense to ask what it means and whether it is possible to melt a time crystal, which basically means whether you can remove the synchronous aspect of this motion that characterizes the phase.
That sounds really interesting. And it's amazing that you're whetting our appetite before the big event even.
Yeah.
You really are becoming a showman.
Exactly. With that, we should start because we can't wait to hear what's going on, what else you have to share. So, welcome everyone to the Science Society today. Thank you everyone for coming, and special thanks here to Sam. And before we start, let me give you a little bit of information about our guest speaker, Dr. Sam Autti. Dr. Sam Autti is a lecturer and EPSRC fellow at Lancaster University in the UK. He completed his PhD in low temperature laboratory in Finland, and he was working on superfluid helium-3. Sam he received in 2020 the IUPAP Young Scientist Prize for a range of superfluid discoveries he made. And currently, he works with the interfaces between classical and quantum physics. And he really would like to answer questions such as, what does it feel like to touch a quantum fluid? And can we melt a time crystal? And whether the outcome is a time liquid. If those are not the coolest questions in the world, I don't know. For me, they are. And before we start with your presentation, Victoria would like to ask you a couple of questions. And then the stage is yours. Thank you.
Thank you.
Okay, thank you, Katarina. So, Sam, welcome to Science Society. In those questions are so fascinating. They're the visuals that they evoke are just, that's really fun to spend some time considering those questions. So my question to you is to carry us into your research and give us a little bit of a background to your background in science, but not academic. Rather, what is your if you look back through your life, what would be your unique connection to science? Meaning a point at which um, you felt an affinity for sciences in general, and that could be sometime in your in your youth, in play, or sometime in your education. So that is my question to you.
All right. Well, thank you very much for the kind introduction, first of all. Um, as to my inspiration for scientific life, well, I mean, I've always been interested in learning about just about everything that I can learn about. I mean, I've been reading books about not only physics and chemistry and mathematics, but also philosophy and biology and politics and all that, pretty much as long as I can remember. And then if you talk to my parents, I guess they could list certain like early signs, such as when we went to visit some family friends, I would normally go, like, as the first thing I would go to the kitchen to like open the doors which are lead to the space under the kitchen sink to see what kind of pipe work there was, or something like this. So um, I guess this kind of like technical approach to things is very natural to me. Well, maybe I could also share a story about how I became a superfluid scientist instead of something else. So this was I was a student in what is now known as Aalto University, but was actually Helsinki University of Technology at the time. And so there you apply for summer positions in research groups during your first or second summer, and I did that as well. And then in the end, I was choosing between two groups in the Lotem lab, and both of them were working on superfluids, and I didn't understand anything about that. But I had just had this gut feeling that one of them was like very dynamic and interesting, and the other one was somehow not. And I only later I learned that the other one had some like major had some major setbacks in their projects, and so I selected the one which happened to be successful without really knowing why. Um,
Yeah, thank you, thank you. I'm writing this down because it's really every answer is so unique, and both parts of your answer were are so appreciated, and hearing about I mean, both of the things you're following your inclination to be curious, looking under the sink at pipes, and that just continues to build on what you're doing now, and shows how important it is that children are allowed to play and experiment and look around at stuff. So yeah, thank you. And so then yeah, this is great that you followed the path of superfluids. And then can you carry us up into your current research, how you ended up here?
yeah, so well, as I explained, I became a superfluid scientist by selecting a group that was working on superfluids, more or less by, well, semi-accident, if you wish. But as soon as I was in there, I was so fascinated about the combination of, you know, the variety of everything that was involved, from practical aspects like soldering things and building pipe work and like real hands-on experiments, to the very complicated theoretical aspects which have to do with helium-3 especially. Um, and the people doing like or sharing their expertise in that. I mean, I'm an experimentalist, but I do my best to understand something about the theories as well. And so then, therefore, doing a PhD on this topic was kind of very obvious to me. And really, then after a PhD, there is this tradition in Finland that you can't stay in the same university if you want to continue in academia. And low temperature physics, especially ultra low temperature physics, which is, I guess, the most accurate subcategory, isn't really available in too many places, even on the kind of international scale. So there's a handful of places in Europe, a couple of universities in the States, maybe 3, or well, potentially 4, but certainly no more than 5, and a few in Japan, and that's basically it. I mean, there's certainly less than 20 groups worldwide. And if you're looking for a postdoc position, well, then this will be narrowed down quite a lot by the availability of suitable projects at that particular instant in time. So this is how I basically came to Lancaster. And well, Lancaster has been a good place scientifically, and recently I won a fellowship for starting my own group here. So that seems to be the way things are rolling at the moment.
They're rolling well. I was just curious because of your proximity to Manchester, if you were a Man U fan, but we won't let that interfere with you discussing your work. So at this point, thank you so much for carrying us along through your path, and you are welcome to deliver your talk now. And if you would prefer to have a Q&A at the end, then that's great. And if you would prefer to have questioning along the way to drive your discussion, then that's entirely up to you. And your PDF is pinned at the top so people may follow along. So I need to hop out of this talk for a while, but I want to thank you so much, and the mic is yours.
Okay, thank you very much. Well, please do ask questions while I'm talking, if that is somehow conveniently possible. But if you don't, I will just keep going through this presentation, and we can discuss whatever you wish at the end of it.
All right, thank you so much.
Yep. Well, you're not going to need the slides at the very beginning, but later on when I talk about the experimental machinery and how things actually look like in practice, then you may want to have the PDF available for yourself. Because in the first slide I've just got some photos and some notes for myself to remember what I should talk about. Right. So the one possible place to start a history of time crystals is about a century ago. Is about a century ago with a Russian scientist called Lev Landau, and Landau with some co-workers came up with the idea that phase transitions, so transitions from, for example, a liquid to a solid phase of a certain material like water, that these phase transitions are conveniently understood in terms of the symmetries that are broken in the transition or at the transition moment. Now, this is at heart, this is a very technical, a very mathematical way of seeing things. But the basic idea is to look at the well, in the case of liquids and solids, to look at the characterizing difference between the two and to come up with the simplest mathematical way of describing that. And so that in the case of a liquid to solid transition, what happens is we can take the liquid and look at point A. Then we can moves in any random direction and look at point B, and the liquid will look exactly the same. When the liquid solidifies, this will cease to be the case. And so then we're going to have to move by a certain distance or a multiple of this distance, and the distance is known as the lattice constant. So it's the distance between the atoms in this systematic structure that forms the solid. And so this is the transition from one of these to the other one is called symmetry breaking, because the symmetry of being able to continuously move around and nothing changes to you have to move by discrete steps is mathematically called symmetry breaking. And it has to be spontaneous in the sense that there is no external enforcement, so we're not placing the atoms in some sort of rigid grid, they just want to organize themselves in this way, in very layman terms. Technically speaking, this means that the expression for the energy of the system does not contain anything that intrinsically favors such a structure. Well, then in 2012, so about a century later, Frank Wilczek was applying this idea, and in my mind what he was doing was he was looking at a catalogue of known symmetry breakings in like experimentally explored phase transitions, which is pretty complete. So almost everything that you can imagine is also realized in some natural or laboratory system. But one is not, or it wasn't at that time, and that is time translation symmetry. So what this means is that if we look at a collection of matter in which is organized in a certain way at moment A in time, then it will look exactly the same, assuming it's in some sort of ground state, so like lowest energy state. It will look the same at any given moment later on. In other words, similar spontaneous breaking of this translation symmetry wasn't known in any system. And he was asking the question whether it would be possible to come up or construct a system where this translation symmetry is broken. And he called that a time crystal in a mathematical reference to space crystals, so ordinary crystalline solids, where the same thing happens in space instead of time. Okay, so that's so much about where the idea came from. Well, very, very quickly it was then realized that what he has described, so basically a phase of matter where particles keep moving synchronously and periodically without external enforcement, it was very quickly realized that this actually makes a perpetual motion machine, in layman terms again. So, and that should tell you that it's impossible to make a system like this. Well, I mean, that's a curious coincidence, considering that what the research publication that this presentation will end up with concerns experimental studies of time crystals. And theoretically speaking, the excuse that, well, one excuse we can use is that quantum physics is weird, so it's actually okay if things keep moving forever in some certain period, or with some certain period, as long as we can't see it. And so if we go and observe it, so meaning we create a measurement that is coupled with this motion, then the motion should start leaking energy and will eventually disappear. Right. Then from an experimental point of view, putting the same, or there's another excuse we can use, which is that the mathematical structure of physics is so strong in many cases that we can actually afford to only kind of approximately fulfill the conditions for a certain, well, in this case, new phase of matter. And things will still work reliably. And in a combination of these two, then we can experimentally create time crystals. And while you could argue that then this is kind of trickery and why do you bother, it actually turns out that this is theoretically a powerful approach, and it will allow us to ask things like whether we can melt time crystals, which I will return to. But of course, there's a certain aspect of, a good sci-fi name doesn't hurt when it comes to gathering attention and getting your things published. So I mean, that's a factor which is there, undoubtedly. Right. Well, I'm now moving on to page 2 in the PDF, where I have some experimental figures of the machinery, if you wish to follow that document. Okay. So shifting gears a bit, I'm going to talk about how do we actually do this in practice. So the system we are using to create time crystals, the underlying system is called superfluid helium-3. Helium-3 is a rare version of helium with only one neutron, whereas helium-4 with 2 neutrons is the stuff that you put in balloons and so on. Well, for our purposes, helium-3 is much more interesting because it turns out it will have intrinsic structure that, as an example, will allow creating time crystals inside the superfluid. But it has the downside that you need to cool it down to ridiculously low temperatures before it turns into this superfluid that is a prerequisite of what we want to create. Namely, we need to get it down to at least a thousandth of a degree from absolute zero, and we'd prefer to be close to a 10,000th of a degree from absolute zero. And that's not very easy, can be done. And what we'd use for that is shown in the figure in the picture on the right. So this is a nuclear demagnetization cryostat. There are maybe 20 of these things of different varieties in the world. And, well, it's unrelated to the project I'm now talking about, but this one is actually rotating, so you can see that this whole thing is spinning around its axis in this photo. And it turns about half a turn per second in this photo. Just as a kind of a funny technical curiosity. And while it's doing all that, it cools our superfluid to about 100 microkelvins. And how we do that is shown on the left. So this is the inside of the cryostat. What is the part which is shown is inside the blue vessel in the right photo, which is a thermos container for liquid helium-4. So this the whole thing on the left is immersed in liquid helium-4, and so that is a liquid which boils at 4.5 Kelvin, 4.5 degrees above absolute zero, and that's kind of the starting temperature of the cool down process. After that, which you can't see in this photo, there's a container inside the bit. There is the horizontal steel-colored bit at like the 1/5 down from the top, above the label which says steel chamber, or the arrow which points to the steel chamber. And so this all that then down from there will be covered by a vacuum can. So this is a steel can which isolates, which allows us to pump the inside to a vacuum. And then there's a sequence of cool down stages. First of which is known as the 1K pot. So this is a chamber where you use a powerful vacuum pump to force helium-4 to evaporate. And so if we keep the pressure down, then the temperature in this chamber goes to about 1.5 Kelvin or something like that. And then the rest of the machine between the still chamber, which is, well, its long name is distillation chamber, I'll come back to that in a minute, and what's known as the mixing chamber, operates using a funny phenomenon, which is that if you take helium-4 and helium-3, so these two stable isotopes of helium, and you mix them, you force them to be mixed, which happens in the mixing chamber, then this mixing process will decrease the temperature of the mixture without any lower bound for the operation of this process in temperature. And to facilitate this mixing process, there is a distillation chamber where we pump helium-3 out from the system, and the two chambers are connected via a capillary tube. And then there is another tube which feeds helium-3 in. And so what the outcome of this is that we mix the two in the mixing chamber and we separate them in the still chamber. And the still chamber goes to like half a Kelvin, and the mixing chamber goes to maybe 5 millikelvin or something like that. So 5,000ths of a degree from absolute zero. So that's not enough. And after that, what we do is we take a large chunk of copper, high purity copper, which is called the nucleus stage, which here is covered by a brass shield, so you can't see the copper actually. And then we put that in a very high magnetic field, let's say 7 Tesla or 8 Tesla magnetic field. And the copper then is cooled down by the mixing chamber until we close this connection or remove the connection. And then we ramp the magnetic field down. And the outcome is that the nuclei in the copper cool down as proportional to the change in the magnetic field. So if they start from a few millikelvin, they can easily go to a few tens of microkelvin at the end of the process. And if we connect this to the superfluid sample, then we can cool the superfluid to maybe 100 microkelvin. And so this is how we get the experiment facilitated. Well, if we move on to in the PDF file, you will see what the experiment itself looks like. So on the right, there is a photo of the real experiment. So in the middle, you can see this 15 centimeter long glass tube. It's quartz glass, which is about 6 millimeters in diameter, and that is where the superfluid goes. So this is filled with liquid helium-3, and then it is connected to the nucleus stage at the bottom of this figure via some powdered silver surface, which it has an enormous surface area for the purpose of maximizing the thermal conductivity between the two systems. Okay, so that was somewhat technical, but I think it was probably entertaining to most of the audience. This brings us to where the experiment itself starts. So on the left, you can see a Povray representation of this same glass tube, where the coils that are used for facilitating the experiments are also shown. So these have been removed from the photo on the right. And then, without going to too much detail about what's going on here, we organize a trapping potential. So basically, a spatial arrangement for two time crystals to be placed in by a combined effect of tuning the magnetic field profile and moving the surface of the superfluid to a suitable location inside the tube. And then the time crystals themselves, they are made from magnetic quasiparticles. So these are essentially intrinsic excitations of the superfluid, and they're called quasiparticles for the reason that they behave like particles, but you can't take them outside the superfluid. So therefore they're not particles without the quasi, but otherwise the difference of these things and particles for the purposes of our experiment are non-existent. Okay, and these particles, they correspond to, if you want, their quanta of spin waves in the liquid, which means that they are basically little magnets which are spinning, and because they are doing that, you can then couple to them. So you can observe this motion by bringing in coils made from copper wire, which are shown these brown NMR coil things in the picture on the left. And what will basically happen is that the magnetic field will be constantly changing, and this will create a voltage in the coils, and then we bring wires out of the cryostat, and we put this voltage into a recording device, and then it appears on the computer monitor as a sine wave. Well, in reality, there's a very complicated system for removing noise and amplifying the signal and isolating everything from the environment, and some resonator circuits for again amplifying the signal, and some lock-in amplifiers for removing certain frequencies, and various other things that you probably don't want to know about. But that's basically what is done. And then the little magnetic quasiparticles, these magnons, they to use one theoretical tool or language, they form a Bose-Einstein condensate, which means that they are quantum things all doing the same thing. So they are all spinning the same way at the same speed and within 1 BEC. And because they are moving this way, and because they are moving periodically, although the system doesn't contain any hint as to what this period should be, then this also makes a spontaneously moving periodic system that one can observe. So therefore it is, experimentally speaking, a time crystal. What we do here is we couple the system kind of weakly, so the lifetime of it will be relatively long for quantum stuff, so it can be, well, you can push it to half an hour, but more typically it would be maybe 10 minutes or 5 minutes or something like that, which is extremely long considering that most quantum systems, even the ones where people actually want to extend the lifetimes, the coherence times, as much as possible, would be dying out much faster. I mean, orders of magnitude faster. Okay, so we've got time crystals, and we know how to observe them, and well, the basic methods to create them have been explained, as well as the theoretical motivation. Well, what did we actually do then in this research work? Well, if we move to page 4, so the last page in this PDF file, there are some examples of the measurement data and analysis from the paper itself. Now, I will not discuss much of the mathematics or the analysis or the technical conclusions we draw, but I will kind of, in some sort of overview, I will try to explain what's going on and why we believe this is what it is and why it is relevant, before then trying to kind of explain in some sort of broader context what the conclusions may be. Right. So a time crystal can exist as long as it is not interacting with anything, which is to say, as long as we are not observing it. And if we start observing it, it should start disappearing. So then we can ask the question, if we take two time crystals and make them, quotes, observe one another, then doesn't it mean that they must also start disappearing? Well, it turns out it doesn't mean that. And it can also be done in practice, and that's exactly what we have done here. So we took two time crystals that were actually shown in the previous slide, or in this computer rendered picture. And we took these two time crystals and we made them touch one another. And if you make two quantum objects touch one another, then there are certain very specific predictions from the machinery of quantum mechanics that tell you what you should expect to happen. And one of them is that that if there are two systems, they will form a so-called two-level system, which is not a very creative name. But what it means is that you get this like phenomenology and toolbox of this kind of Hamiltonian, if you wish, which will make certain predictions. For example, if you try to make the energies of the frequencies of the two constituent levels cross, then the stuff that you can observe will just avoid crossing. And and this picture, which you can see here, if you analyze it carefully, I mean, so what we're looking at here is basically a frequency decomposition of the measured signal from the coils. This is the top right figure in the last slide. And so we see these colored peaks which are moving in time. So those are the two, the bulk and the surface time crystals, if you wish. And the observed frequency of the lower frequency state continuously moves, and there's no obvious crossing with the higher frequency. And then with some complicated analysis of the frequencies and couplings, and there is other things which are shown in the analysis plot on the left lower corner, we can indeed confirm that they didn't cross and that everything works the way expected. For example, that particles are moving between these two states, which are seen as this, what is labeled as the sideband in this plot. Okay, well, I could keep talking about the contents of the paper for a long time, but I think I won't do that. If you want to learn more, you can ask me after I've finished this introduction.
I thank you so much for this really interesting introduction and how you set up the experiments to create these time crystals. That's really interesting. So thank you so much for that. And yeah, if you open for questions, please flash your microphones once you have a question on Jamie. I know you were waiting, so please go ahead.
Hi, Doctor. Thank you so much for that talk. It's a wee bit mind blowing, and there's a lot of stuff that I don't really get. But one question I do have: when you were describing before how to get the temperature as low as you were talking about,
Yes.
I was trying to get my head around that. When you were talking about adding was it helium-4 with the helium-3? Yeah.
Yes.
Is this will sound so dumb, but is this a little bit like how when you put ice into water, it makes the water colder? I mean, obviously not the same in terms of like anything like, but um, was you trying to put were
Well,
you
it's
mixing
not
these?
very far from that, in that it is indeed if you wish, a thermodynamic process which follows the mixing, and the outcome of the thermodynamic process is that temperature drops. And so, if you want a kind of a relevant back of the envelope picture of how this works, basically, helium-4 is doing nothing because this temperature is very low for helium-4 already. And so what this means is that when we bring helium-3 in, it will expand into the space which is essentially emptiness. And then if we expand a gas into a larger container, it always cools down. So this is what the helium-3, why it ends up cooling down the system in kind of semi-classical picture. Of course, the quantum mechanical picture is a bit more involved, but it's not very far from this hand-waving idea.
Really? Is that the idea of is it like I think I remember something like heat itself is just the vibration of atoms or something. So when you talk about filling in the spaces, are you talking about filling in the spaces so much that there's even less movement for them, so there's even less heat, or am I completely misunderstanding?
Well, you don't need to go to quantum physics or any Brownian notion. You can just think about the kind of simple-minded, large-scale observation that if I have gas in a small tank, and then a valve, and then a big tank, and I open the valve so that the gas from the small tank goes to the empty large tank, then what happens is that the gas gets colder. And that's just the way thermodynamics of ideal gases works. And so that's not very far from why helium-3 cools down when you expand it into a volume of helium-4. Although that sounds kind of wild.
That does. Honestly, I'm finding it difficult to get my head around. That does sound quite wild. Thank you.
Gilbert, did you have a question? You unmiked, or was it Dr. Shah? Yeah, go ahead. We cannot hear you, Gilbert. Not sure. Can anyone? Is it on my side or?
We can hear you fine,
No,
Katrina.
I can't hear.
Okay. Dr. Shah, did you have a question? Or Katie?
I have another one if no one else does.
Okay. Yeah, then I'll go after you. And then George also joined the stage. Okay, go ahead, Jim.
Okay, here I am again. So I was having a look at your paper, and there was a part I was wondering if you could explain a little bit, please. It was the part about the two time crystals interact with nonlinear feedback.
Yes.
I don't understand much of that at all, but could you explain what linear feedback is for me, please, and maybe what nonlinear then would be would make more sense to me, please?
Okay. All right. Right. So usually a two-level system, so the simplest two-body quantum system that you can have, doesn't have any feedback, which is to say you externally set the parameters of the system and then the evolution follows from that. You may be changing them in time, but regardless, they are somehow externally determined. Then you can have linear feedback, which means that the changes imposed depend on what are happening in the system rather than on what the experimentalist is how he's turning the knobs in the lab. But this linear means that the effect is always proportional to the cause. And then nonlinear feedback is the same, but the connection to the cause is not it doesn't have to be proportional to what is causing it. So it's just more complicated, and so therefore results in a richer potential set of physical phenomena, if you wish. And so in the case of this experiment, the feedback means that in all the experimental figures where you see that, say, for example, the frequencies of the things observed are changing, they are changing because the frequencies depend on the population of the time crystals. And this is a kind of a complicated feedback mechanism which has to do with how the superfluid underneath everything, all of this is behaving. And so therefore, what we do is we put a certain number of magnons to both the states, and then it's hands off from that moment. So then everything is happening just because of the intrinsic logic of the system. If that's basically what the nonlinear feedback means.
Wow, that's actually quite incredible. That's thank you so much for answering that.
Yeah, thank you so much again. And I wanted to ask, so so I read that you can, since you link two time crystals together, it would maybe open up for the future a way to use this for quantum computing. How does it? Because we learned on a talk we had here before and from you that you cannot really, like, time crystals oscillate work while we basically don't disturb them, right? We have to isolate them, and as long as they don't produce any work, it kind of works. But did that change since you linked the two together, and will it open up a possibility for using this this system for quantum computing?
Yeah. So well, there are different aspects to the answer to that. One of them is that on a kind of general conceptual and capability sort of level, and even maybe theoretical understanding, the problem of observing and not observing a time crystal is very closely related to the problem which you face in, like, one of the most common problems which you face in, or challenges which you face in building a quantum computer, which is how do you control the system when you want to control it, but avoid disturbing it otherwise. And so in this sense, from a kind of a technological perspective, learning how to do one will also tell us how maybe the other one can be done. And this is actually reflected in recent developments in time crystals, because some of the most recent works have been done using what you might call prototype quantum computers, or systems that people study for eventually the aim of creating a quantum computer. And then if we go to technical detail, well, maybe a time crystal could be used as a memory because it lives so long, or something else. So that's really kind of like very far-fetching speculation. And it would be, I mean, for a blue skies researcher like myself, it would be much more natural to try to, if we have to speculate, to speculate about what may be the fundamental consequences eventually, or if you're allowed to dream, then what would you dream about? What would be the consequences of the research eventually? And so here, one potential answer, which I actually forgot to talk about during the introduction on this first part, is that there are really big problems in modern physics which remain to be solved. And one of the most famous ones is that we don't know how you continuously get from quantum physics, which describes small systems, to classical physics, which describes the everyday experience. The continuum between the two worlds is kind of conceptually incompatible. And well, these large quantum systems, of which time crystals are one example, sit between the two worlds in many different ways. And so therefore they allow studying the interface between these two things. And so maybe by studying time crystals, then eventually as an example, if we learn how to melt a time crystal, then it takes us one step closer to classical physics from this kind of coherent or synchronized time crystal world. And so maybe then by doing this consistently, we can learn how the classical and quantum actually join up in the middle somewhere.
Oh, that's very interesting. And so you have to kind of keep the system really isolated, if I'm correct. So
Yes.
so are you so if if you if you let leak some type of little interaction, like how fast does it disrupt, or does it continue going? Do the oscillations continue going on for a little bit, or does it depend of the factor, or does any leak basically of interaction immediately disrupts this oscillation?
Well, that depends on how you organize things, but the way they are organized in the current experiment, each time crystal contains a large number of particles, which is to say, it can leak for a long time before it completely disappears. And indeed, the experiments we do, we actually continuously record what the time crystals are doing. So that's why you see these continuous traces in time in the paper, in these, well, technically these are windowed Fourier transforms, but basically they are these things where time crystal shows as a frequency peak in time in these color maps. And that means, so, and well, that's basically because the coils we use for observing the time crystal are there all the time. In principle, it would be totally possible to take the coils out for a while and then bring them back mechanically when we want to check what's going on. And in assuming we'd at the same time make the system very cold, I mean, as cold as it can be made, basically, then there would be hardly any leakage, if any. I think the longest lifetimes that have been observed were close to half an hour or even exceeding that. And that it was still with some smaller coils in place, I'm pretty sure. So in principle, if we take the coils out, I mean, if you put your hands in and remove the coils, then the system is basically living forever from the perspective of how fast other things are happening in this system.
Yeah, I have one more question that I asked Dr. Pedro before, but since you go to this blue sky thinking to make assumptions, from the quantum to the macroscopic world, like my thinking was that if time crystals make this connection, would this support the hypothesis that we don't have like one big bang, but more like a bouncing back, that like our universe keeps oscillating if it is an isolated system? I know that's really far-fetched, but I like thinking about these far-fetched ideas.
I don't think it has anything to do with that, but I could be wrong. Yeah, so I mean, in slightly more theoretical terms, as I said in the very beginning, we have good reasons to believe that time crystals, in the strict sense of something which moves forever and which you can still go and see, cannot be created and will never exist. And so, in this sense, it's kind of a physicist's adventure to laboratory experiment which goes close to some interesting theoretical concept, but you should keep in mind that it's done for the benefit of our understanding of physics, accepting that this necessitates certain compromise about what you can actually do in like general reality. And then when it comes to stretching everything to cosmology, well, there are multiple obstacles conceptually between quantum physics and cosmology. For example, general relativity is not compatible with quantum physics either. I mean, let alone classical physics with quantum physics. And so this means that making predictions in the region of the history of the universe where both of these are simultaneously needed is not something that we can currently even like discuss, because we know that, so to basically to explain to describe large gravity, high density of mass, if you wish, which is definitely the case in the region close to the Big Bang, or even relatively far after it. And then bringing that together with quantum physics, which is also definitely the case, not only in the Big Bang, but also, for example, at the surface of a black hole, which is kind of much less exotic than the Big Bang from the present day perspective. That this is not something that can be actually done reliably. And if you start digging, there will be contradictions, and that basically tells you that one should be very careful. Whether the universe repeats itself while it is, I don't think it's related to time crystals, is a very interesting question, but unfortunately, current theories are fairly unable to speculate about that on any kind of level of credibility.
Okay. Yeah, my thinking was that you have basically a macroscopic system based on, that the behaving in a quantum way, that it would be an oversimplified model, basically, of what on a large scale happens. Like, we always go back to very simple models, like
Yes.
a squid for a human brain and
Yes.
stuff like that. It was oversimplified, but yeah, thank you for explaining. I appreciate that. I see that Ashkat and Dr. Shah, you didn't ask a question. Please go ahead.
Hello, Dr. Sam. It was a great presentation, and really appreciate your time here. Just have two very simple questions because as my background, I'm not into theoretical physics as much. But I just wanted to. My first question is, you had mentioned about the coils, the SMR, NM. This was the NMR coils, and you had explained that um, because of the use of these NMR coils, you were able to capture the analog signals, and you were able to gauge the sine wave that was basically projecting on your computational devices. And you had also explained that you were using certain kinds of noise reduction techniques and other aspects to make it more comprehensible. So I just wanted to ask, while you were doing this, did you what kind of findings were you getting without all those noise attenuating devices that you included so as to capture the comprehensible frequencies? So what kind of observations were you facing without the attenuation devices and SNR reductions?
Right. Well, I guess I would start the answer from the fact that a cryogenic experiment like this takes a very long time to prepare. And so therefore, if you want to change something, I mean, as an example, you cool down the system, you change something, hands-on, and then you put everything back in place and start to cool down, and it's going to take you about a month before the experiment will be ready to start. And you will have used, I don't know, 10,000 pounds of electricity to run the system. So it's not something that you do very often if you can avoid it. And with this background, we never really measured or even tried to measure the signals without sophisticated signal handling technology, for the simple reason that they are very small and you wouldn't really see much. However, all the individual components can be tested on their own, and we know exactly what they do with like trivial input. And also we can turn off the physics in the system by, for example, emptying the sample container completely and then measuring what the amplifiers do on their own to an input signal. And so we are, in this way, it's kind of very straightforward to understand what the circuitry contribution is. And so we're very confident that what the measurement yields in the end is just the real physics and nothing but the real physics. To give you an idea of the kind of components which go in, we start from the closest bit to the experiment. Well, this is going to be slightly technical, but so you've got these coils, and then they have inductance, which means that it takes a certain amount of energy to create a magnetic field using these coils. And then if you connect them, the wire that goes to the coils, to a capacitor, which is an electric component, then this combination will have a resonance frequency. So a frequency at which it will effortlessly oscillate if you want. And this can be used to amplify the readout from the coils, because the resonator will kind of be more willing to accept that frequency than any other frequency. So any phenomena at that frequency will be very visible, while all other things will be kind of suppressed, and which is very handy. Then there are, after that, then there are lots of very annoying and very tedious components, some of which are in the cold bits of the thing and are made in the lab for this particular purpose. And it took some poor PhD student probably a few years to create them, which are all needed to make the signal large enough, not because we can't measure small voltages, but because inevitably the environment will be radiating noise into everywhere, and so then this noise will be just simply larger than what you're trying to measure if you don't do all these things before that.
All right. Thank you very much for that explanation. My second question is, you have used helium-3 and helium-4 in order to observe the time crystal and its behavior. Uh, in the future, what other material or what other types of elements you think would be best suited for a similar kind of experiment? And how much do you have, you may not have conducted the experiment yet, but what kind of idea or belief you have that it may uh, take par with the similar kind of setup and the experiment?
Oh, that's an interesting question. Well, first of all, from the technology perspective, the cool down methods which we acutely need to carry out any of these experiments are highly dependent on various material properties of not only helium-3 and helium-4, but also many of the metals and plastics which are used for various purposes in the construction. And usually these materials are more or less irreplaceable. So, for example, the cool-down process can hardly be done with any other elements other than helium-3 and helium-4. And so that's for the continuous cool-down stage. And then, I don't know, the metals which are used for building the cryostat are things like copper and gold and silver and a few other things. They are very carefully selected, and they are used in a very carefully selected sequence, and that cannot be changed either without losing some of the performance. So that's unlikely to change. Then when it comes to the sample itself and the physics, well, helium-4, first of all, is used just as a workhorse, so it never enters well, in this experiment, it doesn't enter the sample container itself. It's just for cooling things down. And when it comes to helium-3, well, that's actually one of my favorite topics. So helium-3 is a very unique physical system. And while the reasons why this is the case are a bit convoluted, I can explain that, but it will take me a moment. The consequences are easy to explain. So this system has it's a quantum system with a very rich internal structure, and the consequence of that is that it is conceptually and mathematically connected to seemingly very distant fields in physics, such as cosmology and high energy physics, particle physics. For example, the Higgs mechanism, which everybody has heard of, was originally actually a superfluid idea, and it was known as the Anderson mechanism before Peter Higgs and fellows applied it to the Standard Model, and well, that's what it is now known for these days. And so with all that, it's for this particular kind of research, there are very few alternatives, and so therefore it's unlikely that I will switch to any other kind of physical system anytime soon. Because, well, and also because I do this very well and don't know much about other things. But I mean, that's a kind of a practical reason. Maybe I could try to explain why this diversity appears, although I'm not sure I'd be able to do this in a comprehensible way. But so when you form a macroscopic quantum system, you're going to need a phenomenon called condensation in general terms, which means that all the atoms, all the particles that make your system needs to be in a single quantum state and doing the same stuff. And then nature knows two different types of particles. There are bosons and there are fermions. And well, this is one of the weird consequences of quantum mechanics. And so bosons can readily all be in the same state, but fermions simply cannot. So if you try to make fermions go to the same state, then quantum mechanics will tell you that this cannot happen. And helium-3 is a fermion. So in order to turn that into a superfluid, something extraordinary needs to happen first. And this weird thing is pairing up of the atoms. So another peculiarity of quantum mechanics is that if you pair up fermions, then they become bosons together. And while pairing up certain things like electrons in superconductors is straightforward because electrons don't occupy any space, they're point-like particles if you wish. pairing up helium-3 atoms is not easy because they have actually a size. The atom has hardcore repulsion with other similar atoms if you try to push them very close to one another. And then via some theoretical detours, this ends up meaning that the pairing state becomes very complicated. So the way you form these pairs is very complicated. And this very complicated implies that the quantum mechanics of the outcome of the resulting system basically contains just about all the physics, theoretically speaking, that there is. I mean, that's a slight exaggeration, but not much. And which makes helium-3 a very interesting topic to study because suddenly, when you're carrying out an experiment, it may actually be telling you something about cosmology instead.
Interesting. Thank you so much, Dr. Sam. And it was, a small little masterclass that you've given, and many thanks on that.
Yep, thank you.
That actually is truly mind blowing. I have another question for you, and I'm sorry if this sounds too simple, but I saw that when in the paper when you were talking about the two like coupling up the two time crystals, you could extend the life or the observational life up to, is it 1,000 seconds? I think you said in here. Um, uh, what is it happens that why only 1,000 seconds? Is it because it gets too warm? It heats up too much, or what's the reason for that?
Right. Well, where should I start? Well, I guess when a physicist reads 1,000 seconds in the quantum context, I mean, and especially for a coherence time, which this basically is, then that's I mean, typically you would be reading about milliseconds or something like that. So this is a very long time. Um, why it is not infinity? Uh, there are two known reasons, and maybe new reasons would appear if we pushed it far beyond what we have done so far. But two known reasons, and they are the following. The measurement apparatus around the system will, due to the way, well, fundamentally because of how quantum physics works, if you're observing the system, then in this way, then energy will go out. Well, I mean, we could speculate about removing the observation, and that's technically speaking not difficult in principle, at least to imagine how this would happen. And so then we just have the quasiparticles, these magnons, in the superfluid, and everything else is very far away. So this leaves an intrinsic mechanism for the removal of magnons, if you like. And that has to do with thermal excitations of the superfluid itself, and basically, well, if you like, collisions with these thermal excitations, which are a different type of a quasiparticle. And this will be suppressed exponentially. This is the technical term, so very rapidly when temperature is decreasing. Meaning that if we decrease temperature from what it was in these experiments, we could easily suppress this effect by orders of magnitude within a certain not so wide range of temperatures. But inevitably, it's never going to be zero. However, it's kind of a similar vein as accepting that some of the systems that you're studying to understand theory better may be just an experimental kind of reflection or realization of something which we can't really make in the lab. For example, time crystals, or even Bose-Einstein condensates, they are similar in this fashion. Physicists tend to think that if something disappears exponentially, then in this region where it is very small, it is just as well to call it zero for the purpose of understanding how it works. And also theorists will tell you, if you ask them, that that zero doesn't exist. So I mean, there is always coupling between everything, and it's only if it goes to zero very fast that you can, in practice, say that it doesn't exist. Yeah.
Thank you very much. That's absolutely fascinating.
Does anyone have more questions? I know we've been going for over an hour, so maybe we can ask one or two more questions to respect Sam's time here. Thank you for giving us, all this time and answering all this.
My pleasure.
Dr. Shah, anyone else?
Yes, I mean, I want to say thank you so much. I was a little bit late at the beginning. So my question from you is about, we know that about the, state of the energy, especially when we are talking about the time crystal, they are mostly in a lowest energy state. But however, they have a repetitive motion. And my question from you, because we know that they are not losing energy to the environment as well. Do we have any environment, or, by today, that somehow just break this kind of behavior in the long term or not?
I'm not sure I fully understood what you want or what you were asking, but let me try to answer anyway. I didn't go into detail about the theoretical complications around time crystals, but we can do it now because that would be a part of the answer. So I said earlier that, or referred to at least earlier, that this kind of perpetual motion is okay in quantum physics if it cannot be observed. And indeed, there are systems where it never stops and it doesn't leak anything, and we can't observe it. So, well, okay, you can ask whether it exists in any kind of reasonable sense, but if you take an ordinary, I don't know, superconductor, so certain, this is a wide range of metals, for example, which become superconducting at a low enough temperature. So if we do that, then this superconductor will be described by a large-scale wave function, and a part of the wave function is a phase. So this is basically the direction of the complex number that the wave function is, if you like, and in the complex plane. And that direction will be rotating forever. So this is perpetual motion, which doesn't leak anything, and it will never stop unless the system warms up too much and the superconducting state is destroyed, therefore. But we also have no hope of observing it directly or indirectly. And so this is why the intuition of this kind of or the reference to the classic weirdness of quantum physics, where observations matter, is actually so useful, because it really turns out that you can do both. You can have a system which doesn't decay and you can't see it, and you can do a system which does decay, but it will only slowly do it if you observe it kind of very carefully. I'm not sure whether that answered your question in any way.
Yes, and so in this case, because you just explained, when we have two time crystals, do you still need that, do that rotation? Because you just talk about rotation and changing the angle.
Yes.
So okay.
Yeah, well, that's an interesting question. And the short answer is that nothing changes if you bring in two time crystals. So the total number of magnons in them is not changing, is not decaying any faster because of the connection between them. That's the short answer. The long answer is that we don't know how large we can make the time crystals, or rather what kind of stuff we can connect to them before the decay process becomes a necessity. And this is a very technical way of saying that we do not know when quantum physics will turn into classical physics, because between quantum systems this kind of decay is not necessary, but between actual measurements, so human observations, and quantum systems, it is needed. Add many technical details around this, but this is kind of the very rough outline of our current understanding of it. Yes, and this is an open problem. Nobody knows what the answer is. And as a side note, one of the possible outcomes of quantum computer research, which is very well financed and many people are working on that, so there's a good reason to believe that something will come out of it. One potential and very interesting outcome is that they may find out why quantum computing is not possible. So that's a possibility. And if they do, then it's very likely that this will tell us what happens at the interface between classical and quantum, which would be fantastic from the perspective of fundamental physics, and maybe not so great for the companies investing in this, but well, that's life.
Dr. Sam, I just wanted to, just ask one small thing, and I'll just shut up. The thing is that you mentioned in your experiment, you had observed that the time crystals have, periodic sinusoidal, observations. So, was there any aspect of quantum entanglement, the aspect of quantum entanglement that you could observe, or do you feel that there was an aspect related in the experiment?
Well, the short answer is no, there is no quantum entanglement, but I will elaborate on that a bit. So generally speaking, another aspect of this classical to quantum question or set of questions is that these what we call macroscopic quantum systems, so large-scale quantum systems made from a large number of particles, they do not form entangled states, or at least forcing them to do so is extremely complicated. And so in this experiment, that doesn't happen. Well, then as a side note, I might say that the Hamiltonian, so this mathematical description of this two-level system that we study, is nevertheless one-to-one, kind of like mappable, so corresponds one-to-one to the description you would use for a small two-level system made from two atoms, for example, or whatever. Well, maybe not atoms, but states in let's say, a superconducting circuit. And that is including the superposition states that a small system Hamiltonian describes. And the superposition states in a small system map to states with different numbers of particles in this large system, mathematically speaking. But that does not mean that in this large system these states with different particle numbers would have any quantum character beyond that contained in the two-level Hamiltonian. For example, you cannot create, what shall I say, any of these weird long-range effects that entangled states will come with, where if you measure one state, it has implications for the other one somewhere far away. That is not included.
All right. Thank you.
Yeah, thank you so much for asking all these questions, and thank you so much, Sam, for spending almost an hour and a half with us and
Yeah,
asking.
it was a lot of fun.
Yeah, I hope you enjoyed it, and this was so interesting. Um, it's so far from what at least I do, so it's more fascinating for us maybe because you work in this field every day, but for us it's very fascinating. So
Well, I
we
mean,
will.
I have to admit that you do get used to the things. It's very slow, but you do get used to them. But it doesn't mean that we are not kind of, at least on a weekly basis, very entertained by the outcomes anyway. So it's kind of a privilege to to be allowed to do physics in the lab.
Oh, that's great. Yeah, yeah, I'm glad to hear that. I always in between my job, I also feel like I get paid for my hobby. Like, so
Yeah.
yeah, so yeah, I'm really glad to hear that. So people, please join physics and sciences. you you
Yes.
you be curious and figuring out problems if that's your thing. Yeah, go into sciences. I think currently you have a shortage of postdocs. So yeah, if you go into the field, you will get the job for sure. The pay is not, depending on where you live, not the best, but you keep working on something that you're really intrigued by, which is another thing not everyone gets to do. So
Well, I
thanks.
mean, it's true that the pay is not like you would get in some industry, and well, most obviously these times it would be a quantum computing where they will certainly pay you more, but well, at least on the kind of best days, then the freedom which you get in exchange for that is very unique, which is, I guess, one of the main motivations for people to stay in academia.
Yeah, and you're allowed to publish, right? You're allowed to go to conferences in industry many times. You're not to do that. You're not
Yeah.
allowed to talk about what you do, and yeah, you don't travel as much for work and collaborate. So it's very different. I agree. It's yeah. So well, thank you for
Fascinating.
sharing, and we
Yep.
wish you a lot of funding and
Well,
that
thank you.
that good luck for your own lab. You shared earlier that you're um, getting your own lab probably so soon. So good luck for
Yes.
that.
Well, my own group, of course. The lab contains more people than just me, but yes.
Your own group, yeah, and that you get
Yeah.
good people and that everything works out. So and yeah, thank you everyone for coming and asking questions. Oh, Kyle, he has uh I didn't it didn't work to bring Kyle up. He had the question, but maybe Kyle you can. Oh, is it? Yeah, please share.
No, no worries. I just wanted to say thank you. I already put your next talk on the calendar. And just for fun, how many realities are there? Is there one ultimate objective reality? Or are there several multiple realities? Just for fun.
uh, I I guess this is a reference to the interpretation problem of quantum physics. What shall I say? I don't believe in the multiple worlds interpretation. That's kind of not an option to me. And now that you mentioned that, there is, I would say, relatively recent work that is, experimental work, which is relevant to this problem, which seems to indicate that also the famous Copenhagen interpretation, which basically says that you need to calculate and shut up and don't ask any stupid questions. That this interpretation is also wrong, but it's going to take me a lot of time to explain what that means, so maybe I will spare that for the next time.
Yeah, for those general questions, we had the guest speaker here a couple months ago, where he works with protons and inner protons, how they are entangled. Anyways, he's also experimental physicist, and his experiments showed that the universe is most likely non-deterministic, which made me very happy because I hated the thoughts of otherwise. Yeah, if you're interested in these type of questions and talks, check out our recordings and also join our discussions here. And yeah, thank you, Kyle, for asking that. It's an interesting question. And thank you, Sam, for for sharing your knowledge and your time with us. I really appreciate it.
Thank you.
Thank you very much for this talk, Sam. I know in the replays I'll be picking through this for a long time to learn more and more each time. Thank you so much for this. Thank you.
Oh, you're welcome.
And mad respect for your PTR, the captain hat. Love
it. Well, that's actually a hat which you get when you go to a Finnish tech uni. So the white stuff, the white hat you get from for graduating in a high school, and then the tailpiece, which you can see on the left, is added when you go to a technology university.
Okay, good to know. I remember being in Porto, Portugal, and saw a lot of people. I was like, oh, wow, there are a lot of Harry Potter fans around here, but it was actually just the uniform for school, so yeah. It looks sharp anyway.
Yeah, I agree. It looks very cool. Thank you for having that PTR. And thank you again. If you like discussions like these, join the club, Science Society. We will have 2 guest speaker events tomorrow morning at 9 a.m. EST. We'll have Dr. Jill talking about his latest publication, multi-omic rejuvenation of human cells. So it's research about rejuvenation, which is quite interesting approach. And then we'll have at 9 p.m. EST in the evening, joining us from Japan, Dr. Atta's model of a time machine to study ancestor galaxies' life cycles. So it's about how our universe was back in time and galaxies in the earlier stages of the universe. So thank you, and thank you again, Sam. We really appreciate your time, and I hope you come back one day, maybe with some updates. And okay, thank you, everyone.
Okay, thank you.
Thank you, everyone. Have a good day.
I dropped out for a second. I'm sorry. My app is freezing. My microphone is. It's constantly when I text in the back channel, it keeps. I can't hear you, but maybe it's on my side. Oh, yeah,
I can't
I
see
don't know
you.
why.
You're
Whenever
invisible.
I press back and forth between, looking at the Science Society to read out the program and all this different things, when I switch, it always asks me if I want to start a different room. Like, I don't know, that's so weird. So apparently, yeah, I couldn't do anything in between. So, well, I tried to close the room again. Like, yeah,
I still don't see you. I think, Katerina, you're in the parallel universe right now.
yeah, maybe.
So, shall I close the room then for you? So you
Oh,
can.
yeah, if that works for you, thank you.
Okay, you count and I'll close when you say I
Okay,
don't. Okay.
yeah, let's do that. 3, 2, 1. Bye, everyone.